So today I want to talk about algebra. And I learned algebra 2 times. First time, high school, equations, expressions. And then I learned about algebras in category theory. And these are called F-algebras. And they were like completely different. I had no connection between what we call algebra in high school and what we call algebra in category theory. And then there's in between high school algebra and category theory, there is programming. And in programming, algebras come into play when we talk about recursion schemes. Maybe some of you have heard about recursion scheme. Well, you definitely heard about folds, right? Folding stuff. That's like the simplest recursion scheme. And it uses an algebra. And usually we don't talk about the place where algebra sits inside a fold, but it is like, if you want to generalize it, like folding not just a list, but a tree or some more complex data structure, then suddenly, you have to understand that you are actually doing algebra. But this is a different kind of algebra. And then at some point it clicked, that these two notions of algebra actually have a common root. And it's just one is a generalization of the other. So today I will talk about how we get from the high school algebra part all the way through data structures, recursion schemes, some simple recursion schemes, and category theory. And hopefully this will be like an intro into category theory that's not too hard to understand because we approach it from the perspective of programming. So we have these expressions, like x squared plus 3x plus 4. This is what we understand as algebra, right? How do we form expressions like this? And how we evaluate expressions like these? There are 2 parts to algebra. And that's it. That's just it in a nutshell. So as programmers, we look at an expression like this and we say, how do I parse something like this? I will parse it into an expression tree, right? So I have a plus, okay? So this plus will be a node in my tree and it has 2 children, x squared and 3x plus 4. Okay, but what is x squared? Well, I have to recursively erase this thing, right? And say this is really a product, a multiplication of x times x. So I have the leaf nodes in my tree that are variables. And this is again a plus. Okay, so I'll replace this with plus. And one child is 3x, so it's a multiplication, it's a product of a constant 3 and the same variable x, variable of the same name, and then finally plus constant 4. So this is a data structure. So now we are looking at it from the programmer's point of view. We have a data structure, and we can encode this data structure in a language, in Scala, for instance, right? The second part of algebra is the ability to evaluate expressions like this, right? So if we evaluate an expression, we'll have to substitute something for x and do the addition multiplication. And again, from the programmer's point of view, we can look at the tree and say, okay, how do I evaluate this tree? Well, we'll evaluate it like bottom up, right? So the first node, so what is 3? 3 is a number, let's say a double, right? What is x? X is a variable. It's a string, right? We have to assign a value to it. So we'll come up with an evaluator that says, well, let's substitute 5 for X, right? Now we have the node. So we'll multiply this value, 3, with this value, which will be now 5. So 5 times 3, I guess 15, right? And then we go here and we do plus 15 plus 4, Then we evaluate this, 5 times 5, 25, right? We add the result, and at the end, we get the result, which is a double. So we know how to form things using trees, data structures, and we know how to go over these data structures. And again, both things are recursive. The data structure is recursive, and the evaluation is recursive, right? If we have a deeper tree, we have to go deeper into this. So Oli will now write in Scala a data structure corresponding to a tree like this.
To write a recursive structure, we will start with select trait expr. The first case class const will represent constants and will have one parameter, double. This case class extends expr. The second one, variable, has one parameter string to represent the name of the string of the parameter. The case class times is a binary node of the tree. It has two parameters, both of type of expr, which represents the recursivity in our tree. So we have non-recursive leaves, constant var, and recursive binary nodes, times and plus. Let's encode our example. X times x plus 3x plus 4.
So this particular expression, x squared plus 3x plus 4, now in the form of a data structure, can be written as, more formally, this is a plus node. It has two children. One child is the times node, right? The times node has two children, and one child is variable whose name is x, right? Another child, it's also a variable, types x. So this kind of the writing, the drawing of the stuff in a two-dimensional way is much more readable to us humans than writing code. So this is a very nice exercise. So this is plus, and we have times. Okay. We have const 3. So here's a double, right? Here we have variable x. Again, the same x as here. And finally, we have const 4. Okay. And so this is a graphical description of the code that Oli wrote on the computer.
Let's evaluate this expression. An obvious choice to evaluate this expression is to turn it into a single double value. We evaluate bottom up, starting with leaves. A const leaf can be evaluated to the value it contains. For evaluation purposes, the variable node can be assigned any value of type double, for instance, 5. In general, we can write many evaluators, or we can define an evaluator that is parameterized by the value of x. To evaluate the nodes, we have to first recursively evaluate the children nodes producing values of the type double. As you can see, we call eval and then do the operation on it. Finally, let's evaluate our expression and see the result. So the result is 44.
So we decided to evaluate this thing to a double, but there are other possibilities. We can, for instance, evaluate this tree to a string, sort of a pretty printer for expressions. How would we do that? Well, we would replace the const 3 with a string 3, right? So a string 3.0, let's say, right? We know how to convert numbers to strings. We would leave variable as x, and then we would just combine these things into nodes by concatenating strings and putting operators in between them. So why don't we do that?
Let's implement what Bartosz said, the pretty printer. So as you can see, it takes the parameter expr and returns a string. The rest is more or less the same. We pattern match on expression, and for each of the case, we produce a string. In case of const, it is evaluated to a string representation of the double it contains, a variable leaf to the name of the variable, and the nodes are evaluated recursively. Again, we call pretty on them and then concatenate them using the operator, left side and right side, and then we will get a string.
So now we have two ways of evaluating this tree. One is evaluating it to a double value, and another is to evaluate it to a string. But in principle, we can evaluate a tree. If we have a way of traversing a tree and turning nodes into values of some type, and it can be an arbitrary type. Some of these ways may not make much sense, you know. These were the sensible ways that we demonstrated, but you know, there are like infinitely many ways of traversing a tree and turning it into value, and there are infinitely many types of values that you can extract from a tree. I mean, we could do this for vectors, matrices, complex numbers. These are the ways that make sense. Lists, whatever, any data type. Okay? The problem with this is, if you look at these evaluators that we have implemented, they combine, they mix two different things. The turning of the nodes into values and combining values is one part. The other part is doing the recursion, the traversal, right? The traversal is done by doing recursion. It's like every time we were evaluating a plus node, we had to say, well, let's first evaluate the children. That's the recursion part. Then once the children are evaluated to, let's say, to double, then let's add these two doubles. Or if they are evaluated to a string, let's concatenate these strings with an operator in between. So we would like to factor out these two things. Do the recursion in a most general way, once and for all. Like this recursive part can be encapsulated into one thing, and then the particular way in which we are evaluating and combining values, that's another part. And this other part will be called the algebra. So the way to factor out recursion from this picture is to define a data structure which deals only with one level of this tree. So for instance, we can define a data structure that deals with leaves, right? So leaves are like non-recursive parts by definition. But the next level, what do we do with nodes? So instead of having a node that has children that are also trees, we can say, let's have a node like times, but with children that are just like arbitrary type R. Okay? And when we are doing the evaluation, then we could say, well, let's replace R with double, and we'll have two values of type double, and when we evaluate, we'll just multiply them. And when we have plus, we'll replace it with a node that has two values of the same type R. So when we are doing the evaluation, we'll replace this with double, let's say, and we'll have values of type double. We'll multiply. Here we'll add them, right? If we replace R with strings, then we do the concatenation here with times, concatenation with plus, right? So this data structure that's parameterized by R can be described as a non-recursive data structure. And Oli will now introduce the non-recursive version of this tree.
Let's copy our previous result. We'd like to create a data structure that would have placeholders for the results of the evaluation of the children. To do that, let's parameterize our expert by the result type, R. The leaves have no children, whereas the nodes do. So we replace expert with R. In the original recursive definition, the children were full-blown expression trees. Here they are replaced by values of some general type R. We also need to rewrite our evaluators. Let's start with eval. Essentially, it does almost the same thing, except it has a different parameter which we are going to pattern match on. The const and variable stays the same, but for plus and times node, what we're going to do, we're going to get rid of this recursive call, because we know that the types of the parameters are already evaluated to the needed type. Same goes for pretty.
So we've had these two evaluators, one evaluating to double, another one evaluating to string. And we could, there are functions that turn doubles into strings, like toString, right? toString. Can we use this function to transform one evaluator to another evaluator? How would we do that? Well, there are two ways of doing this. One way is take the evaluator, the double evaluator, evaluate an expression, and then apply toString to it, and you'll get a string. The other way of doing this is take an expression and apply toString to the contents of this expression. So for instance, take a node plus f with two doubles and turn these doubles into strings. And then apply the other evaluator, which is the pretty printer evaluator. Okay? And see if you get the same result. But what does it mean to apply a function to the content of a node? It means that this data structure has to have a way of mapping functions to the contents of the data structure, right? And this is called a functor, a data structure that has this property that you can implement map, which we also say a map is lifting a function. So we have a function like toString, right? Map will take toString, lift it so that it can be applied to an expression and produce a new expression. So it takes an expression of double and produces an expression of string. So let's see if x per f, our data structure, is a functor. Can we implement map for it?
To write a functor, we're going to use a cats library, which conveniently contains the functor class. First, we need to import cats and cats implicits. Then we need to define an implicit val of type of functor of x per f. And then we need to implement the map function. So what we need to do is to just pattern match on fa parameter and decide what we do in each case. We don't have to do anything with the const leaf and variable leaf, but for our nodes, we need to apply the function f to the left right side and the right side. So as you can see, plus f, f, l, and fr, which will return f of b at the end. Let's look at simple example. We have one expression. It's an operation plus on two constants, and we want to evaluate it. What we do is we call eval f on plus f, and then we call a pretty printer on plus, but we map it over to string. As you can see, the results are not the same. In the first case it's 3, in the second 1.0 plus 2.
So now we are ready to introduce some definitions. So this combination that we were using, we pick a type and we pick an evaluator that evaluates this type. This pair is called an algebra. So if we pick a type, let's call it A, an evaluator is a function that takes f of A to A. You can call it, let's say, A. And the algebra is the combination of this type and a function. This type is often called the carrier type, and the function, the evaluator, is called the structure map of the algebra. Okay, so let's write down the definition of an algebra in Scala for a given functor f.
We could introduce a type alias algebra, which is parameterized by two parameters. The first one is a f, which is higher-kinded type, and a, our carrier type, and this is equals to function from f of a to a. And we need to rewrite our evaluators again. That's pretty simple. We need to change the name, of course, and then we change the type of the evaluator to algebra x per f and double in case of eval f. The shape is almost the same, except we don't have input parameter now, so we can just remove these lines. The same Please stop the video and just look how simple it is to refactor all these things. We can do the same for any algebra that we have, just simply changing the return type to algebra and leaving the same evaluation type, string in case of pretty printer.
So now let's talk about these mappings of evaluators. And so they actually become mappings of algebras, right? So if we have another algebra that evaluates to some different type, B, right? So we have an evaluator B, lowercase b, that evaluates f of b down to b. If we have a function that maps A to B, then we can apply this function after evaluating fa. We take fa, this expression, evaluate it down to A, and then apply this function. Or we can first apply f to the contents of this expression using map, right? Because it's a functor. And in category theory, we just write it as f acting on f. Okay, so this is the lifting of f by a functor f. This is really what we call map in Scala. And if this diagram commutes, what does it mean it commutes? Like, this is how we say it in category theory. We say the diagram commutes if these two paths give the same result, right? So one path would be f after a, right? The composition of these two functions. First we perform a, then we perform f. It's written in categorically as f after a with this little circle. Must be the same as b after f. Well, categorically we just say ff, right? Without the brackets. So this is the commuting of this diagram means that these two compositions of functions are the same. So now in category theory, we operate on these diagrams because it's easier than writing equations. And with these diagrams, we can do things like combine multiple diagrams together. So suppose that we have like a third algebra, you know, f with a carrier c, right? And the evaluator c down to c. What if we have two such functions, f from a to b and then g from b to c, that satisfy this commuting condition? So it means that this diagram, fg here, also commutes. So if this diagram commutes and this diagram commute, if we combine them together, we get that this path gives us the same result as this path, which means that g after f is also a mapping of algebras. It maps this algebra to this algebra. Okay? This algebra to this algebra. So we have a composition of these mappings. Now these mappings of algebras in category theory are called Algebramorphisms. So Algebramorphisms can be composed together. And moreover, there's one more thing that we can say about them, that there is an identity algebramorphism. What is an identity algebramorphism? Well, we'll take an algebra fa, a to a, right? fa to a, And identity algebramorphism would map this algebra to itself. So we'll write the same algebra twice. Okay. And there is an obvious function from A to A called identity, right? Now, we can lift identity using a functor. Now, functor has this property that it preserves identity, it preserves composition and preserves identity. So lifting of ID is again ID. So this diagram will automatically commute because ID after A is the same as ID before A, right? Whether you apply ID before A or after A doesn't matter. So these two things together tells us something, that you can compose algebramorphisms and there is an identity algebramorphism. When you have some structure like this that has composition and identity, it's called a category. Okay? So algebras form a category. Why is that important that they form a category? Because now we can apply some ideas from category theory to this. And the first idea that we can apply immediately is that in a category we can define something called an initial object. In this case, we are talking about a category of algebras, so we will be talking about an initial algebra. An initial object is an object that has an outgoing morphism to any other object in the category. Translating into algebras, it means an initial algebra is an algebra that has an algebramorphism, and in fact unique algebramorphism to any other algebra. And you might think, okay, is that really possible? Because we've seen that there's like most of these simple functions between carrier types, they are not algebramorphisms. Like toString was not an algebramorphism. We had to think hard to find an algebramorphism that was the like make done, right? But it turns out that these algebras that are formed using functors on types in the category of types and functions that we use in programming, that these algebras, they do have initial algebras. And these initial algebras are very important. And with these initial algebras, we can do really interesting things. So let's see what an initial algebra, what property does initial algebra have in terms of these diagrams. So let's say that we have, that the carrier of the initial algebra, we'll call it capital I. So this initial algebra will be f of capital I with an evaluator that evaluates it to I. Okay, and we'll call this evaluator J. We don't know what it is yet. Well, we'll find out. Okay, the property of initial algebra is that if we have any other algebra, so let's say FA evaluates using A to capital A, then there is a unique morphism from algebramorphism from I to A. Let's call it M, such that this diagram commutes. The lifting of M here. Okay? And you might think, okay, what is this initial algebra for our expression? Like we have this functor x per f. Is there an initial algebra for this functor? Turns out that the initial algebra for this functor is actually the same thing as the one we started with. Remember the x per, the x per data structure, that was the recursive tree, recursive expression tree. Turns out that the recursive expression tree is this I, the initial algebra. And if you have this recursive expression tree, you can always find a morphism that goes into any other algebra. And you can ask the question now, okay, what's the evaluator for this initial algebra? Like, how do I turn, x per f? So x per f is this part here. X per f acting on I, and I, in our case, is x per, the recursive thing. How do I turn this into x per? That's the evaluator j, right? It turns out it's very easy to implement. So the interesting thing about j, the implementation of j, is that it sort of does nothing. It just repackages data from one form to another, takes a double into double, string into string, and takes a node with left and right into a node of left and right. We just give it a different name to this node, right? So because it's repackaging things, it actually is invertible. It's like we can repackage from left to right, and we can go back from right to left. And this is a very interesting property. And it's actually a theorem. It's called a Lambda's lemma, which says that the evaluator, or the structure map for the initial algebra, goes both ways, has an inverse. It's called an isomorphism. This fact that J is an isomorphism, we can write it as f acting on I is isomorphic to I. Isomorphism means that there is a mapping one way and its inverse going the other way. And it means that for all intents and purposes, fi and I are the same. And we've seen in the implementation of J that it's actually like repackaging stuff. So it's a different way of repackaging the same information, right? And this equation has a name. It's called a fixed point equation. It means that I is a fixed point of the functor f. What does it mean? It means that a fixed point is something that when you act with a functor on it, you get the same thing back, right? It does not modify it. It's a fixed thing. You transform it and you get back the same thing. So it's a fixed thing. Like f acting on any other type will produce a different type. But this one, it actually produces almost the same type up to isomorphism. So this is called a fixed point equation. And it turns out that this fixed point equation can be very easily written in a programming language, in Scala. So here's the definition of a fixed point of a functor in Scala.
To convince compiler, we need to create a case class, fix, which is parameterized by fix, which is also parameterized by something, which will have unfix of type of f of fix of f. And this is possible because it's a case class, and case classes do allow to contain a recursive definition. We also create a companion object with two functions, in and out, which together form an isomorphism. As you can see, they go from f, fix f to fix f, and fix f to f of fix of f. We also create a type alias x with fix of f and a bunch of helper functions.
So now we know that this initial algebra is actually given by the fixed point of a functor. So we can rewrite this diagram here using the fixed point. So we can say f, our f acting on fix f, or in Scala, right? Brackets. It evaluates to fix f, and the evaluator is called in. Okay, because in was going from f fix f to fix f. It also has an inverse, which was out. Okay, Lambek's lemma says that this is an isomorphism. But because this is an initial algebra, then there is a unique Algebramorphism, M, to any other algebra with a carrier A. So here's f of A and some evaluator A, right? This is the lifted M. Which is actually map M, right? It's the map lifting of M. And now if we look at this, okay, if we look at this diagram, there are two paths in it. Let's forget about in for a moment. Okay, let me erase this in and concentrate on out. What it says that M is the same as out followed by map M followed by A. Let's call it algebra. Okay, this is our algebra. So we can write it as a recursive equation, M equals, and I write it in the form, categorical forms like alg after Fm after out. And if we call M kata F, kata alg, then we have an equation, kata alg equals alg after F of kata alg after out. Okay? And we can write this formula in Scala.
To implement the categorically, we will have to write the function kata, which is parameterized by f, which is functor, and a, which is our carrier type. It takes algebra as a parameter, as you can see in the formula kata alg. So we write the same, which is parameterized by our functor and a, and it returns a function which goes from fix f to a. So we start with a fix, and then we reverse this categorical expression because we're going to use, instead of after, we're going to use and then. So we start with out, then we go to our functor, call map on it with the recursive call of categorically, which takes an algebra, of course. And then we move to algebra and apply the fix parameter. This is it.
So now that we have implemented this kata, this is a catamorphism, it's called a catamorphism. A catamorphism of this algebra, we can ask the question like, okay, this is a recursive definition, right? Does this recursion terminate? This is like a well-founded recursion. And the answer is yes. Because what it does is, it first applies out to an expression. So we get this recursive expression, the fixed point expression, right? Which is a complete tree with children and children of children and so on, right? When you apply out to it, you strip like the external constructor from it, so you expose the top level node, right? If this is already a leaf, then you're just exposing a leaf, and that's a simple case. But if you're exposing a node, then you apply lifted catamorphism. You take the catamorphism, you apply it to children of this node, which are complete trees again, right? But the children of a node are smaller than the whole tree. So this recursion actually is applied to smaller and smaller subtrees. And eventually it terminates when it hits a leaf. This is a well-founded recursion, right? So this evaluates the F kata, evaluates the children by mapping catamorphism onto children. And then we get this top-level node with evaluated values, and we can apply the algebra to it, which just combines these values. So the algebra is the way of combining the values at a single level of a node, right? So now we can rewrite our evaluators that we have introduced earlier and the algebras that we define for these evaluators. We can write these evaluators as catamorphisms.
How do we evaluate our expressions? We could apply kata to our pretty algebra. And to see the result, let's apply it to second expression. We could do that for any algebra. For eval f or any other. You can find the code on GitHub which has the same type. Enjoy!
So let me summarize what we have done. We start with a functor. This functor can be used then to define a recursive data structure. In our case, this was a recursive tree, expression tree, but it could be anything. It could be a list, could be a tree, could be whatever functor you come up with can be used in this construction. So we have a functor, and this functor sort of describes like one level non-recursive part of a recursive data structure. And it's much easier to deal with these non-recursive data structures. And we can define evaluators that are non-recursive very easily. Then we have this orthogonal direction, which tells us how to create recursive data structures from these non-recursive functors, right? Using fixed points. So this is how we define like trees, lists, and so on. And once we have this, we can then apply this algebra, this single level evaluator, to a recursive data structure, full-blown recursive data structure, using a catamorphism. And this catamorphism is implemented once and for all. You have it in the library, you can use it. So you can plug in a functor, you can plug in a particular algebra, and you get an evaluator for a recursive data structure. And this is the power of this approach. Thank you.